Thank you, Bastian, for letting me come here. We met in 2019. I was doing some hemispheric work and he knew a lot about Africa, so it was great to talk to him. And now that I'm visiting Reading, or I'm in Reading, I thought it was a good opportunity to visit and discuss some more. So today I'm going to talk about this last work that we submitted last week, actually. And the main focus is summer rainfall changes in Southeastern South America, but hopefully I'll convince you that the storyline approach, which is the way that we address regional climate change, is useful for the region that you study or for regional changes in general. So to motivate, these are two figures from chapter 10 and chapter 12 from the latest IPCC report. And I'm showing this for two reasons. One, to show this is a typical way in which results are shown for regional changes. So this is showing a percentage of area in land regions where there's a robust annual mean precipitation change. So basically robustness here is associated with the amount of models that agree on the signs of the change, and I'm going to talk about that in a moment. But what I want you to first notice is that the globe is generally separated into different regions, and sometimes when we separate in these regions and in this way, we end up having conclusions that are very large scale when we want to focus on one region, like for example South America. Variability in precipitation actually is much more local, and as I will try to show you, changes are also much more local. So when we actually want to show robustness in results and in projections, if we stick to ways of representing the uncertainty or the robustness in this way and averaging over large regions, we end up being able to say, well, quite little. So my approach is an alternative to this. And then here we have from chapter 12 a figure showing vulnerability. And in particular, in South America, there's vulnerability related to food systems, to cities and infrastructure, and then also terrestrial ecosystems. So mainly because of food systems, a potential drying trend in this region could be of great impact. The observed trends during the last 3 decades have been a robust positive trend in precipitation, however, and that has benefited the region very much because it relies on agriculture to a large extent. So a drying future would be bad. And if we look at this type of way of representing changes, the conclusion that we would draw is that we could expect it to get wetter annually. However, what I'm showing here is results, and what I'm going to show from now on are results based on the CMEP model ensemble. So just in case you're not familiar, the couple model intercomparison project is a project where many modeling centers who developed and run global climate models do these experiments with different emissions for scenarios. And this model output is available to all. This is what we're using. So as I was saying before, many of the conclusions related to robustness are based on models agreeing on some signal. So for example, precipitation. Robust projections in precipitation would be projections for which at least 90% of the model ensemble that we're using agree on the sign of the change. So the stippling here for the multi-model ensemble mean change is a particular stippling showing dark points where the results are robust, so 90% or more of the models agree on design. Open stippling is showing regions where 90% of the models agree on a robust, on a large signal, so compared to noise, to the year-to-year variability. And regions with no stippling mean that there's models where the response can be large with respect to variability or not, but on top of that, the models do not agree on the sign of the change. So basically, some models will say that the projection is a drying, and some models the projection is a wetting. So actually, the only region in this large IPCC box that, as I was showing before, this is the box that is chosen for this region, only this part shows a robust wetting trend. The rest is quite uncertain. All of these other boxes are boxes that have been used in different studies where they study South America. So as you can see, this box is the one that captures and actually was designed to capture this region. This is an example of one of the models that does not agree with this sign of change. And the stippling here is showing that it's a robust response within the ensemble. So these models are normally run, the ones that have resources to do it, to perform many simulations. So this one has 10 simulations. And this is showing that at least 9 of those 9 simulations show drying. So what we would say is that this is not noise or variability or by chance, but it's the actual response to the forcing in the system. So based on this, the questions that we want to answer are, first of all, how do we define a regional box that represents the uncertainty in precipitation changes, specifically related to the large scale? So because, as we'll see in a moment, what we're going to try to do is explain these disagreements in the models based on the disagreement on the large scale response in each model to greenhouse gas warming. So we first want to understand what is the best way to describe this region. Then we ask, are all plausible scenarios for summer precipitation in this region characterized by wetting? And then we ask, can the large-scale remote driver responses to climate change explain these differences? And what we would basically say is that as long as we have a large-scale circulation response that is in agreement or can explain the precipitation trend, then that future is plausible, and we would try to build confidence on the physical and mechanisms and the atmospheric dynamics instead of a statistical measure where actually taking the mean of an ensemble of models that differ in their parameterizations and in what we would call epistemic uncertainty, because they're not samples of the same system, is much more robust, even if that means contemplating the possibility of having 2 different futures. So when I talk about large-scale circulation, what I mean is very large-scale features that we know are responses to climate change. So one of these large-scale features that has been studied a lot is what's called the tropical amplification of global warming. And it's basically an amplified warming in the tropical upper troposphere associated with the enhanced latent heat release in the tropics. So this is a figure from a model experiment by Emmy Butler in 2010, where they performed simulations with a simplified model, just imposing the warming in the upper troposphere in the tropics, and they analyzed what the extratropical circulation response was to this forcing. And what they find is this is hemisphere dependent, and this is 50 degrees is more or less the latitude of the eddy-driven jet in the southern hemisphere, for example. What they find is that this forces a polar shift of the westerly winds. On the other hand, relatively recently, for the southern hemisphere, Paolo Sheppi and Ted, my supervisor, found that in CMAP models and also in simplified experiments, the delay in the end of the spring season for the stratospheric polar vortex in the southern hemisphere, so just in case you're not familiar, the stratosphere has a seasonal cycle with very strong wind in the winter due to very strong temperature gradient between poles and the tropics, and eventually when the temperature gradient starts to break down because of the beginning of the warm season, that circulation also breaks down, and that basically determines what will be the character of the summer circulation in the southern hemisphere. So what they find is that that response is also present in the forcings scenarios or in the climate change simulations. So basically, all the models agree that there's a delay in the vortex breakdown date for a large anthropogenic forcing, but they don't agree on the amount or how large that delay will be, and that can differ in like 30 days. But the response to all is that there's a power shift which is greater if that delay is greater. So this is another very large-scale feature that responds, that's a response to climate change that can affect large-scale circulation. And where I'm going is I will try to show that changes in large-scale circulation can affect changes in precipitation, and that uncertainty in how large these large-scale changes will be can map onto uncertainty in the precipitation change. So synthesizing what I just showed, anthropogenic forcings can force changes in the zonally symmetric tropical climate, which would be the example on the left, and the stratospheric polar vortex. Also, the stratospheric polar vortex has been affected by ozone-depleting substances. So there's actually a combined effect of greenhouse gas forcings, ozone-depleting substances, and in particular in the 21st century, as I will show in a minute, that gives a complex evolution because ozone-depleting substances have gone down since the year 2000. So ozone recovery can lead to the opposite effect in the vortex compared to the effect of greenhouse gases. So all of that is contemplated in our analysis. So to show you what this means in terms of models, basically we have a large uncertainty in what the models do in these two remote drivers. So this amplification that I was showing before and the delay in the vortex can be quantified with two indices, and if we look at the spread in the response in the models, that's quite large. So we're going to try to use this spread to understand the spread in the circulation. So how do we do that? What we do is first apply pattern scaling assumptions. So this assumption is basically saying that the pattern of change in every field, in every model, will be proportional to the warming in that model. And that's basically something that we need to do because on top of the uncertainty in these large-scale features, or what we would say uncertainty in dynamics, there's uncertainty in the thermodynamic aspect of climate change, given that different models have different climate sensitivity. So for the same greenhouse gas emissions, some models warm much more than the others. That is also seen here, for example. So this end-of-century changes in the global temperature. In CMIP 5, it's not as big as CMIP 6, but you can see that there's almost a 4-degree uncertainty. So we're basically going to scale that, assuming this, and work with the pattern of the change. So then represent our results in terms of pattern of change scaled per degree of warming. So when doing that, here X is a grid point and M is a model. So this multiple linear regression is designed to capture in each grid point the sensitivity of the field to each of the remote drivers and the multimodal ensemble mean change. So the maps here are showing the coefficient B and the coefficient C of this regression. And what this is showing is that the response to a large tropical warming is a strengthening of the westerly winds. This is westerly winds and 50 hectopascals. So this red here on top of the climatology would be a strengthening. And here is showing a power shift. So basically the vortex leads to a power shift and the tropical warming to a strengthening. So we also looked at storm tracks. This is by producing a field of tracked storms in the whole simulation, and then we compare end of century and past and apply the same regression framework and find the same thing, that we have higher storm intensity as a response to a larger tropical warming and a power shift of the storm intensity as a response to the vortex. So basically here we're seeing how already we can capture the spread in the model responses for the circulation in terms of these two drivers. And the responses are quite zonally symmetric. Now, one of the things that is most studied for the Southern Hemisphere changes is the changes in the Southern Annular Mode. And this is because the Southern Annular Mode is the mode of variability that captures most of the variance in the summer climate in the Southern Hemisphere, and also it's highly correlated with precipitations, for example, in South America. So some people study changes in the SAM and the associated changes in precipitation in that way. So we wanted to see how our results mapped onto SAM changes before going to precipitation. So basically, if we try to study model uncertainty with this approach, what we can do and what we do is propose that instead of describing future climate as the multimodal ensemble mean change, we describe a set of plausible futures, each of which is associated with a combination of remote driver responses, and what we assess is how different they are. Which, for example, in precipitation would be interesting if one leads to drying and the other leads to wetting. In terms of the circulation, what I'm showing here is actually, this might be helpful to visualize what I'm saying. So what I'm showing is what are the what we call storylines that we select. So this is, each point here is showing a model, and what that model response is in terms of its tropical warming and the vortex response, right? So we're saying that we're going to characterize the uncertainty in this model's circulation changes by showing these 4 plausible futures. And when you look at what that really means in terms of circulation, you see that the most extreme are in this diagonal here. One is a relatively weak power shift and strengthening, and a relatively weak Southern Annular Mode. This is an index called the Marshall Index. And the most extreme is quite a strong power shift associated with a high vortex range and a high tropical warming. So this is one of this is what type of results we can get with a storyline approach. But we can also make these plausible futures evolve in time, so based on the same approach using linear regressions, but here adding the effect of ozone, as I mentioned before. This has a complex evolution during the 21st century. We can show how the storyline approach can help explain the spread in the SAM in time. So here the gray lines are showing each model's individual SAM time series, and the blue and red plumes are showing for 2 plausible levels of warming. So remember that I showed that there's a large spread in the level of warming, the thermodynamic aspect of climate change. And the difference between the dashed and the solid lines are showing how large a large tropical warming and a late vortex response would be compared to a low tropical warming and early vortex breakdown response. So basically, the spread in, say, the red plumes is showing how large the uncertainty is because of the large-scale circulation uncertainty, and the difference between the blue and the red curves is showing how large the spread is because of the thermodynamic aspect of climate change. So basically, what we're doing here is not reducing the uncertainty, but explaining where the uncertainty is coming from. And then if you have reasons to believe that a later vortex breakdown is more likely because you have more physical knowledge on that, then you would trust the upper end of this. So when we looked at this for precipitation, this is basically just to show that we were interested in seeing how these ozone depletion substances evolved and how that affected precipitation. Our main conclusion was that there was not such effect so strong. So here, this peak that you see in the year 2000, and then this bent trend is showing that there's an important effect from ozone recovery in the SAM that we don't really see for precipitation. So basically, precipitation is mainly being driven by greenhouse gases, and probably the effect of ozone is too weak in this period to actually show in precipitation. So having got, ruling out the effect of ozone depletion and focusing only on the greenhouse gas effects for precipitation in CISA, we looked at how these remote drivers actually affected. And basically, because of the circulation changes being different, the precipitation changes are different. So one of them, the vortex, leads to higher precipitations, whereas the tropical warming leads to drying in almost the whole hemisphere. So in this first work, we were describing the hemispheric changes, but we still looked at storylines for the precipitation. And what we find is that although there are quite some differences, and there's some scenarios where the summer rainfall can be much larger than the multimodal and ensemble mean. There's some models that show a weak trend, but all show a wettening. So our conclusion from this was we were missing some large-scale driver, perhaps, that would be able to explain why we have some models that actually show a drying. Basically, what we were saying is that these storylines are not good enough to represent the full spread. So in the year-to-year variability, what we know from the large scale to be very important determining the variability in the precipitation are tropical asymmetries, so basically ENSO-like anomalies. So for that, we started to study what was actually the response of sea surface temperature, because we're interested in SST changes that can trigger waves, or that can be associated with a asymmetric response in circulation. We removed the zonally symmetric sea surface temperatures, which are also highly correlated with our tropical warming index. And we studied the asymmetric sea surface temperature change. This is also done in other papers where this connection is found not only in the year-to-year variability, but also in the long-term changes. And when we looked at this field, we see that there's two main sources of uncertainty. There's another blob here, but this actually is highly correlated with this blob. It's like models that are colder here are also colder here. So basically identify these two regions of uncertainty, and because our method is based on mapping large-scale uncertainty onto regional uncertainty, we are interested in where relevant fields might be more uncertain in the ensemble. So applying the same regression framework as before, we now studied more fields. So this is the sea surface temperature response. As I was saying before, this is very correlated with the subtropical Pacific. So there's the SST response to this index as expected. And this is the response in the SST to this index, so in the east as expected. The interesting thing is that the precipitation change when regressed onto these indices is in agreement with what we would expect with an SST anomaly in that region. And the circulation field is showing divergence in the upper levels, in the regions where we have the sea surface temperature anomalies, and a Rossby wave-like teleconnection pattern that connects the tropics with South America. So I don't know how familiar with the atmospheric dynamics you are, but this is more or less the typical teleconnection pattern that we would trust to be showing a connection, but just in case, we also evaluated the wave activity fluxes, and we find that in response to both, there's a very different pattern, but still both are showing wave activity flux reaching the region, which means that there's a dynamical forcing on the circulation in that region coming from this index. So based on that, we focus on the circulation, the precipitation and regional circulation response. This is how what I showed before, that there's a wetting associated with the vortex and a drying associated with the tropical warming. But for these Pacific warming indices or remote drivers, what we find is that although they both have explanatory power, they have very different responses. Basically, we have this power shift of what's called the South Atlantic conversion zone and very strong wetting in the northern side of this region, and a drying in the tip of my region of interest. And then we have a drying band associated with the Eastern Pacific, but then two wetting signals to the south and to the north. So it's actually quite an heterogeneous response that's associated with cyclonic circulations in the region, which is also expected. So as I showed before we were looking at only this part of our uncertainty space, if you want. Now we're adding 2 more degrees of freedom, and this is where the models fall within this spread in this large-scale responses. Before, we were representing our results by showing 4 plausible changes that were within our confidence ellipse. Now we were actually interested in turning the question around, and instead of showing all the plausible futures, focusing on the wettest and the driest futures and trying to understand what large-scale phenomena led to the wettest and driest. So to do that, we produced a million storyline simulation, so basically a Monte Carlo analysis sampling this distribution. And then we basically find the 99th and 99.9 percentile of the storylines, or the spread that we're able to explain with these remote driver responses. And we find that we're able to represent quite a lot the spread in the responses. So here, this figure is showing this cross-section, basically showing how heterogeneous the responses are. So I'm going to go in order here. So this cross-section is showing, this figure is showing the remote driver responses over this line. The red curve is showing the multimodal ensemble mean, which, as we saw before, it's a strong wetting response. And the different curves are showing the different remote drivers. So, for example, the solid blue is showing that the tropical warming leads mainly to a drying in most of the region, but much stronger in the south. In the south, all of the rest remote drivers contribute with wetting the region. But then when we start going further north, we start to see more complex responses. And in particular, in the northern tip, we have 2 drivers that are leading to a drying, which is the tropical warming and the Central Pacific, and 2 that are leading to a strong wetting. So that heterogeneous response then leads to issues when we want to study this region in a broad way. So what happens when we want to take a more IPCC type of approach, or try to aggregate or build an index for this region, averaging precipitation? What we find is that I'm showing here in blue each individual model responses. In orange are reconstructed precipitation response based on the regression model and the large-scale phenomena. And in green, the Monte Carlo analysis sampling the distribution that I showed before. And what we see is that when we average precipitation over the whole large IPCC region, we do a terrible job reproducing the precipitation. We don't even get the median right. But when we start aggregating over different regions where there's a coherent response, then we start to actually do a very good job, and we can explain most of the spread in the model ensemble with the circulation spread. So going back to the Monte Carlo simulations, what we did was condition on the wettest and driest storylines to see what the responses were. And we found that when we do this over each of the boxes, right, because we have to aggregate over the boxes to select to have a precipitation value, we find that the extreme storylines for each boxes differ. So actually, boxes B through E agree on what combination of large-scale phenomena can lead to the driest and wettest scenarios. But when we go to region F, because of this heterogeneous response, we find that the extreme storylines are actually different and flipped. So for the southern sector of my study area, we have that the wettest response is associated with a low tropical warming and a higher than the mean vortex breakdown delay, and a high eastern and central Pacific sea surface temperature change. Whereas for the region F, so the extreme northeast, we find that it's actually the wettest signal is associated with a strong eastern Pacific, but a relatively cold central Pacific. So basically showing that the uncertainty in the sea surface temperature changes in the long term can have a very strong influence in the future precipitation in these regions, and in different ways. So what would be the worst case or the wettest scenario in one case is not the wettest scenario for the other region. But also, as a final result, if you remember my questions from before, we wanted to see if we could actually explain a drying trend in Southeastern South America. And what we find is that when we have a high tropical warming, a relatively early vortex breakdown delay, and the coldest extreme or the coldest scenario for the Pacific warming, we can actually end up having drying in this region. So that would basically mean that we cannot disregard that option. So to conclude, we first find that the model spread in the CMEP ensemble responses for precipitation in South America can be explained by considering this combined influence of large-scale circulation. There is a remote driver combination that can lead to the circulation changes that are associated with the drying response. So this would mean that from atmospheric dynamics, at least perspective, a drying response for the region cannot be disregarded. And then finally that although there is a tendency to produce and report results for regional change in terms of boxes, these boxes, when we're studying precipitations, but also, I have not shown, but also extreme precipitation, extreme temperatures, which are affected by circulation, the regionalization would be optimal if it were done after addressing the influence of large scale, instead of selecting a region based on, say, political boundaries or something like that. So that's it. Thank you very much.